Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RIT 120, Hydraulics. Today we're going to have a discussion about various fluid conductors, namely pipes, tubes, and hoses. Because we all know by now that a couple valves just sitting there on a floor next to a pump, next to a hydraulic actuator is going to do nothing unless we actually deliver the fluid there in a safe, controlled manner. And how you do that is with pipes, tubes, and hoses. So before we begin discussion about pipes, tubes, and hoses, I want to actually have a really super quick discussion about schematics here. I've previously alluded to this in our earlier discussion on schematics. There's three ways to draw a line. A solid line, that's a working line. And previously, remember I said if it's a junction, there's a dot there. If there is no junction, it's passing over it, or like that with no dot there. Typically, I use this guy for connected, that guy for not connected, because this guy, you could sometimes mess that up. The other thing you might see in schematics is this thing called a manifold. Basically, if you weren't, a manifold is basically several connections coming out of a little manifold block there. Basically, one supply, and you could be supplying several different actuators. And remember, an actuator is a device that turns fluid energy into mechanical energy, linear or rotational energy. So that's just the same on a schematic as having connection 1, 2, 3. You got one in, 1, 2, 3 outs, 1, 2, 3. So you might see something like that on schematics too. So the other thing we have here is pilot and drain lines. Okay, so a pilot line is basically used to, a pilot pressure to activate a directional control valve. Let's say this is a spring offset two-position valve. It's actually pilot pressure from another place in the system that's actually activating that valve. Okay, let's say this is an accumulator, which we may have talked about by now. That's basically when pilot pressure comes to a certain point, it's going to push the valve this way, and that accumulator is going to drain. Okay, so also a pilot is a sensing, as we discussed in our pressure relief valve from P to T. It's sensing pressure upstream via that pilot line. Okay, there's another type of schematic out there. So again, pilots were dashed, drains are dotted. And I will freely admit I'm kind of lazy about this. I typically do dashes. Sometimes you'll even see it in book with dashes. We already talked about internal versus external drains. Here's a pressure relief valve that we are assuming is internally drained, i.e. the drain from the bias spring is going to that T directly. But there's this thing called a sequence valve, which I know we haven't discussed yet, but we will. It needs to be externally drained, meaning there's another connection on it. That external drain should have a dotted line, because remember, that's a separate low pressure, returning to low pressure line. So drain lines are dotted. I know you'll see me draw them dashed. I should actually be doing them dotted. Okay, so again, working line solid, pilot lines dashed, drains dotted. Remember it. Okay, the brief introduction here to fluid conductors, pipes, tubes, and hoses. Obviously, let's just talk about all three of them. You should probably be familiar with them, most of them by now. Pipe, basically, it's inflexible, super strong of the three. It requires fittings and junctions and every single bend. Whereas a tube, it's bendable. It's medium strength compared to a pipe, and it only requires fittings at junctions because it's bendable to a certain degree. A hose is quite obviously flexible. It's the least least strong of the three, and it requires fittings at junctions. Okay, so we're each going to go into each one of these guys in turn. And first one is obviously pipes. So our pipes are quite obviously our strongest of our fluid conductors. Disadvantages, they're extremely inflexible. Okay, so some of the things we want to talk about first is basically what they're made out of. Typically a black steel or a stainless steel. Never going to use galvanized. Galvanized steel, galvanized piping, um, it's going to basically degrade the hydraulic fluid as a result of some chemical interaction between the two. Stainless steel, super corrosion resistant. That's typically very expensive too, used for very special applications. Another disadvantage of a pipe, you got to clean it out. These things are made for a number of different applications in hydraulics fluid, as we are about to learn later on in the quarter. Got to keep it super clean, so that's a problem too. You're gonna have to use some expensive chemical cleaning to clean out the inside of these pipes. So I've drawn a diagram of typical pipe here, and a couple terms that we want to figure out here is OD, ID, and wall thickness. OD stands for outer diameter, OD. Okay, so OD is how you order a pipe. Okay, because as we said before, anytime there's a bend in a pipe, let's say you want to go from here to here with a pipe, you've got to put a fitting there. Well, there's a thread on this end here which threads into that fitting. And again, you're going to put some pipe tape on there and thread it into it of the specific torque that you need. And that's the reason why pipes are ordered in OD, because this fitting can fit all different types of pipes of all different types of wall thickness, as long as, and ID for that matter, as long as the OD is the same. So that's pretty neat. That's why pipes are ordered in OD, okay? So what is ID? Well, ID, quite obviously, is related to a diameter. If O is outer, I is obviously inner diameter. And that's the actual fluid passage, okay? So OD and ID. You can order an OD pipe of a certain size, but varying ID. And that ID, if the ID goes smaller, there's less fluid passage area, but the walls get thicker. And that's because OD minus ID divided by 2 is your wall thickness. Because think of that. There's ID. There's OD. If you take OD minus ID, what's left? This guy and this guy divided by 2. That's the wall thickness. Okay? So let's say ID increases for given OD. What's happening there? Well, increased area, meaning velocity, fluid velocity for a given flow rate goes down. Or we could put more stuff into it at the same velocity. Capacity goes up, but you got to pay for that. Well, if ID goes up, your pressure rating goes down, okay? Because what's happening there is your wall thickness is decreased. I mean, think about it. Here is a standard OD of a certain diameter. 2 different pipes. Here's a ridiculously small ID. Here's a standard ID. Which can handle more pressure? Pretty obviously this. Which, for a given flow rate, is going to have the least velocity? This guy, because that cross-sectional area is increased. Okay, so you have to take all these into consideration when you're designing a system with pipes. Okay, like I said, You're not going to bend a pipe. You're going to go ahead and thread it into a fitting to make any turns. So this is obviously not a good application for a mobile device, but you are typically going to see, or a mobile actuator, or something that's moving around. You're typically going to see a pipe is extremely fixed, stable location that is not going to be moving around, okay? Okay, so one of the things I want to talk about too now is our schedule. You may have heard this before, schedule 40 versus schedule 80 pipe. What this is this is wall thickness, schedule 40 versus schedule 80. Okay, and if you look it up in a pipe specification table, pipe is typically available from like 1/8 of an inch. Here, let's just draw this correctly. 1/8 inch OD pipe, all the way up to 12-inch OD pipe. And there's various steps in there, up to 1/4 inch, 3/8, half, so on and so forth. 3/4, there's a little skip there. Just look up a pipe specification table. Schedule 40 is the thinnest one. Schedule 80 is the thickest one. And there's also 160, and then double extra heavy. Okay, so there is no 160 or double extra heavy for 1/8 to 3/8. But basically, let's just start off with a 1/2 inch here. So a 1/2 inch schedule 40 pipe. What's the pipe OD? 0.84. Oops, what am I doing here? Yeah, 0.84 is my outer diameter. Yeah, I know. It's not really a 1/2 inch. What's the inside diameter? For schedule 40, 0.622. Schedule 80, 0.546. 0.466, 0.252. What that's showing you is, again, is the OD remains the same, 0.84. But for schedule 40, it's 0.62. 0.546 for schedule 80. 0.466. Double extra heavy, 0.252. So, showing you increased pressure rating. Okay, you're paying with loss of the capacity. Velocity is obviously going to increase. You're going to have to go ahead and size these things appropriately. You might have to step up to the next OD size for an increased pressure rating, with a thicker wall if you want to maintain velocity at a certain value. Okay, so again, this is something I'm obviously not expecting you to memorize all of this here. It's just look it up. It's pipe specification table. They're available all over the place on the internet. Perhaps you've heard of it. But what I do expect you to know is that a schedule 40 is the thinnest wall. And as you go up in the schedule, it's the thickest wall. Okay? And as a result of that, the ID goes down. Okay? So the next step is tubing. Tubing is basically an extruded tubular soft metal Um, very similar to piping, except it can actually be bent. And where you're going to find tubing is it's in applications that are not moving, but they do require some bends. One of the ways, obviously on like the back of, here's my simplified version of a boom and stick. Actually, this is a great idea to talk about this. Um, Here's the shoulder joint, elbow. So it's going to be a hose here because it's moving, the shoulder joint is moving, but it's not moving along the lengths of that boom. So that's where you're going to put a tubing. Here's your elbow joint, there's a hose, there's tubing, there's a hose. Basically, tube, tube, but it may require some gentle bends along the length of that boom and or stick. And those hoses at the joints are actually moving. But to reduce the risk of abrasion or anything like that, you're going to put tubing on the outside of it. So on those areas that are not going to be moving but may require bends in it. Whereas if we were to use pipe on this thing, we would have to have a fitting here and a fitting here and a fitting there and a fitting there. So that's one of the advantages of tubing. It's bendable. It's bendable to a certain degree, though. Remember, tubing also ordered as a function of OD and has schedules 10 and 20. And again, what's happening for OD, half inch. A schedule 10 has a certain wall thickness, and a schedule 20 has a thicker wall, smaller ID. Okay, get it? Schedule 10, same OD for 20. Thicker wall, smaller ID. So increased pressure rating, increased velocity for that fluid because it's a smaller cross-sectional area. What was I talking about? Anyways, tubing, when you stick it together, you have to have special fittings, and they're typically known as basically as a flared fitting, a tube. Why am I drawing this thing? It's right here. Well, I'll draw it again. Okay, you got a tube that goes along. It's a cross-sectional area. You've got a sleeve with threads on it. Over it. And then you've got like basically a nut that goes over this. What happens is you need to flare the edges of this thing, i.e. push those edges out ever so slightly. And then screw these guys together, exactly as this diagram has shown right here. So you need to flare this for it to fit correctly. And I highly, highly, highly recommend to you to establish this standard operating procedure. Put the sleeve on first before you flare it, okay? Because it's awfully hard to put it back on once you've flared it. Okay, there's also flare-less fittings, and a flare-less fitting is basically kind of a one-time use thing. Inside this nut sleeve, there is this thing called a ferrule, which slips on over the pipe and the sleeve. Again, using cross-sectional, I'm hopping back and forth between cross-sectionals. And there's the body. So the ferrule is slipped on there. Basically, the act of forcing the sleeve and the body together this ferrule flares it for you, expands that out, and forms a fluid tight connection. Okay, again, one-time use, don't mess it up. There's certain tightening specifications for these. Basically, you're just going to look it up in the manufacturer's flare fitting tightening specification. The other thing, what you want to do sometimes is basically as a witness mark. Here is a connector that you've made. What you do, take a red paint pen or whatever it is, just draw a line on it. Once you've torqued it down to a proper specification, draw a line across it. So when you come back the next day and, whoop, what's going on here? When you come back the next day, that witness mark is moved, you know that you need to tighten that again. Okay, the last of our fluid conductors we're going to discuss, probably the one we're most familiar with, is a hydraulic hose. Hydraulic hoses are used in applications where the lines must flex or bend, pretty obviously. Since we're interested in moving things around, this is what we're going to see a lot of. And as I've drawn here, or copied and pasted here, a hydraulic hose is formed of a number of different layers. The more layers, the stronger it is. So your external layers, typically, oil and weather resistant material. The other thing is too, you need to, if they're working around energized electrical conductors, i.e. wind turbines, the hose should be non-conducting. The middle layers, again, like I said, the more layers, the stronger it is. They're typically like wrapped wire braids inside there, or reinforcement, all sublayers, and they're wrapped in alternate directions. So one's going counterclockwise, next one clockwise. The internal is basically it's got to be a chemically resistant internal layer, the inner layer. It's got to be, for whatever material you're moving around, we're talking about this inner layer, that's the only one that's actually in contact with the fluid. So it says maybe a synthetic rubber, plastic. It's got to actually be rated for the chemical that you are using. Okay, so hoses, there's correct ways and incorrect ways to install a hose. One of the things to remember is, well, actually, here, let's have a super quick discussion about this. We talked about pipes and tubing being ordered in OD. Hoses are ID, okay? So hoses are typically go up in 16ths of an inch, are measured in 16ths of an inch. So let's say, so this is X dash 16th of an inch, whatever that X is. Like if I ordered you if I said, hey, get me a -4 hose, what I'm saying is 4/16 of an inch, get me a 1/4 inch hose. So that's a -4 hose. Okay, and if I said, get me a -8 hose, I want you to get me a 8/16 of an inch internal diameter hose, or 1/2 inch internal diameter. Okay, so a pressure rating for a hose, there's typically a safety factor involved, and the manufacturer for your particular hydraulic system, or the hose manufacturer, is going to give you the safety factor. Typically, 4:1 or 2:1. So let's say you have a hose that can withstand a maximum working pressure of 5,000 pounds per inch squared, 5,000 psi, and it's a 2-to-1 safety factor, the maximum working pressure U, i.e. your pressure relief valve, should be set to is 2,500 psi. Whereas if you had a 4-to-1 safety factor, what's the maximum pressure on your pressure relief valve? 1,250 psi. Okay, so this is pressure rating for that particular hose. One thing to be aware of, hoses are not going to last forever. A pipe is obviously the thing that's going to last the longest, but it's not applicable for mobile applications. So you're going to have to use a hose, you're going to have to replace a hose. The other thing is you're going to have to install the hose correctly. Okay, so there are certain things that you don't want to violate. Don't bend a hose too much. There's this thing called basically a maximum bend radius. I may have already talked about this here. The radius is a function of the diameter, and typically it's 6, maximum bend radius, 6D. So let's say I have a 1/2 inch pipe. The maximum bend radius I can make that is a 3-inch bend. Whereas if I had a 2-inch bend, not recommended, because again, it's constricting that particular hose. Whereas if I had a bigger hose, a 1-inch hose, I need to have a bend radius of 6-inch. Okay, that's a 1-inch hose. Okay, the other thing is avoid excessively sharp bends. Let's say you've got a connector coming off here, and you take a hose, and I'll just take the shortest one possible. No, you violated bend radius rules there. So what you want to do is have a longer hose that goes this way. Avoid excessively short hoses. Let's say you've got a connection to here and here, and you just barely stretch that thing out and make it fit. That's not going to work when fluids are cold temperatures, it's going to contract. So you want to actually have a little bit of give there. The other thing you need to be aware of is those connectors, especially in earth-moving operations. They're exposed to abrasion. Sometimes there's a little spiral wrap protection there, or a sleeve or something like that. Some Kevlar sleeve that goes over those things to protect those hoses. What if you're running the hose next to an incredibly hot exhaust? Here's an exhaust pipe that's really hot. What happens if that hose comes in contact? Yeah, not good. So you want to go ahead and shield that hose with a metal shielding, or shield that actual exhaust hose there, or reroute it. Okay, so obviously your quick disconnects, we've already seen these things a bunch. There's the female end, there's the male end, and these are crimped onto a hose using a hose crimper. And what you want to do, you want to pull that back, insert them. When it clicks down, tug on it on either end, just to make sure that those guys are properly connected. Because the last thing you want to do is be troubleshooting something that does not have fluid flow or is not receiving any pressure or fluid flow, and be troubleshooting a component when something's not properly connected. Okay, that's pretty much it for fluid connectors, pipes, tubes, and hoses. Just remember, pipes stronger, inflexible, hoses weaker, flexible. That's the big take-home point, and all the other particular tidbits we discussed right here. One of the things too is remember, you're not just maintaining the valves and the actuators. The hoses, pipes, and tubing for a system are maintainable items, and you have to keep these things in working condition. If you have a stock of hoses in your supply room, don't have them exposed to sunlight. Don't be hanging them on wire hooks. for extended periods of time, because basically what's happening is it's getting that indentation inside there, and when it's aging over time, that's an extremely, when you finally go ahead and pull that hose out, that's got a weakened location that could potentially burst. Okay, so again, these things are active portions, very necessary components to any hydraulic system, and you got to maintain these things. If you ever see a hose that has developed a pinhole leak and is spraying high pressure hydraulic fluid, by all means, do not attempt to grab that with your hand. You need to go ahead and deactivate the system and fix that hose, because what's happening here is if you grab onto that thing, that is incredibly high pressure hydraulic fluid. Not only is it going to cut you, it is chemically caustic to your body. So maintenance of pipes, tubes, and hoses is essential to the performance and safety of hydraulic systems.